Welcome back, everyone. I hope that by experimenting with the applet, you saw that as n got bigger and bigger and bigger, the difference between the right-hand sum and the left-hand sum went to 0. Now, that's not a proof, that's just looking at it graphically. So let's see if we can actually try to prove this. So the limit as n goes to infinity of this difference. The key thing here is what we've mentioned several times before, that most of the terms in the right-hand sum and the left-hand sum overlap. So what, in fact, is the only term that is in the right, when I subtract, that's going to be left from the right-hand sum? The only term that's in the right-hand sum that's not in the left-hand sum, as we've seen several times, is the very last term of the right-hand sum. What's the only term that's in the left-hand sum that's not in the right-hand sum? That was the very first term of the left-hand sum. Now let's rewrite these using our a's and b's. Because remember, x sub n, what we're trying to do is we're trying to find the area between a and b. X sub n was the far right endpoint. So x sub n is our new name for what in the problem was called b. And delta x, as we figured out, is b minus a over n. Similarly, x0 was the new name that we gave to a. This was the left endpoint of the interval. So that's f of a, and delta x is still b minus a over n. So let's think about what is happening here. N is going to infinity. But what's changing as n goes to infinity? Do a and b change? No. A and b were set at the start of the problem. We're trying to find the area, for example, between 0 and 2. So a is 0 and b is 2. Those aren't changing. How about f of a and f of b? Are those changing as n goes to infinity? They're also not changing, because a and b aren't changing, and we're certainly not changing the function in the middle of the problem, right? So the function f stays the same. So what this is saying is that I can write this as all of this stuff over n. So I can write f of b, I can factor out of b minus a, f of b minus f of a times b minus a. So everything in the top of this fraction is a constant, all over n. So whatever this top of this fraction is, it's a number. It could be 6, it could be 6 million. But no matter what it is, it's some fixed constant, and n goes to infinity. And if you take any constant over n, as n goes to infinity, what's this answer going to be? It's going to be exactly what we hope you saw in the applet. It's going to be 0, which is good news. So what does that mean? If the difference between these two things is approaching 0 as n goes to infinity, what does that tell you about the left-hand sum and the right-hand sum themselves? If their difference is approaching infinity, that must mean that they themselves are what? They themselves are equal. So when you let n go all the way to infinity, it doesn't matter whether you use the left-hand sum or the right-hand sum, you're going to get the same answer either way. And that's reassuring, because if we're using so many intervals, infinitely many intervals, whether we start on the left or start on the right, we should expect to get the same answer. Because remember, in the applet, you saw how the left and the right-hand sum are squeezing the exact area between them. So in other words, if we want to compute the exact area, it doesn't matter whether we compute the right-hand sum or the left-hand sum. Both of these Riemann sums give us the exact area under the curve. And we're going to have a special name to define that, and we'll have that in the next video segment.